Advanced Engineering Physics, Unit 2, Quantum Mechanics, Schrödinger's wave equation and the one-dimensional box. One of the most important achievements of quantum mechanics is the formulation of Schrödinger's wave equation. This equation plays a role in quantum mechanics similar to that played by Newton's laws in classical mechanics. It provides a mathematical description of how quantum particles such as electrons behave and allows us to determine their allowed energies and wave functions. To understand the quantum behavior of electrons in solids, we first consider the simplest possible model, namely a free electron moving in one dimension without experiencing any external force or potential energy. In quantum mechanics, physical quantities are represented by operators. The linear momentum of a particle is represented by the operator minus IH cross d by dx, where h cross is Planck's constant divided by 2 pi. The classical expression for kinetic energy is p squared divided by 2m, where p is the momentum and m is the mass of the particle. By replacing the classical momentum with the momentum operator, and assuming that the potential energy is 0, we obtain the time-independent Schrödinger wave equation for a free particle. The equation is written as minus h cross square divided by 2m multiplied by the second derivative of psi with respect to x equals epsilon multiplied by t. Here psi is the wave function of the particle, also called the orbital in the case of a single electron system, and epsilon represents the allowed energy of the electron occupying that quantum state. Solving this equation gives us both the wave function and the corresponding energy eigenvalue of the particle. A particularly important application of Schrödinger's equation is the problem known as the particle in a one-dimensional box. This model describes an electron perfectly confined within a line segment of length L. The ends of the box are assumed to be infinite potential barriers. Since the potential energy outside the box is infinitely large, the electron cannot exist there. Therefore, the probability of finding the electron outside the box must be 0, which means the wave function itself must become 0 at the boundaries. These conditions are called boundary conditions and are expressed mathematically as pi of 0 equals 0 and pi of L equals 0. The wave function must therefore form standing waves inside the box, just like waves on a stretched string fixed at both ends. Only those standing waves that fit an exact integer number of half wavelengths into the length of the box are allowed. As a result, the acceptable wave functions are given by pi n equals a sine of n pi x divided by L, where a is the normalization constant and n is a positive integer called the quantum number. To determine the allowed energies associated with these wave functions, we substitute them into Schrödinger's wave equation. First, differentiating the wave function with respect to x gives d psi by dx equals a multiplied by n pi divided by L multiplied by cosine of n pi x divided by L. Differentiating once more yields the second derivative as minus a multiplied by n pi by L whole square multiplied by sine of n pi x divided by L. Since a sine of n pi x divided by L is simply the original wave function pa n, the second derivative can be written as minus n pi by L whole square multiplied by pi n. Substituting this result into Schrödinger's equation gives minus h cross square divided by 2m multiplied by minus n pi by L whole square multiplied by psi n equals epsilon n multiplied by psi n. The negative signs cancel, and the wave function appears on both sides of the equation, allowing us to isolate the energy. The final expression for the allowed energy levels becomes epsilon n equals h cross square divided by 2m multiplied by n pi divided by L whole square. This result is one of the most significant conclusions of quantum mechanics because it shows that the energy of a confined particle is quantized. Unlike classical physics, where a particle can possess any arbitrary energy, a quantum particle confined inside a box can occupy only specific discrete energy levels determined by the integer n. The energy is directly proportional to the square of the quantum number, which means the energy levels become increasingly spaced as n increases. Another important consequence is the existence of zero-point energy. The quantum number n cannot be zero, because if n equals 0, the wave function becomes identically zero everywhere, implying that the electron does not exist inside the box. Therefore, the lowest possible state corresponds to n equals 1. This means that even in its ground state, the electron possesses a finite amount of kinetic energy and can never remain completely at rest. This minimum non-zero energy is called the zero-point energy and is a purely quantum mechanical phenomenon with no counterpart in classical physics. In summary, Schrödinger's wave equation provides the fundamental mathematical framework for quantum mechanics. When applied to a free particle, it describes the allowed quantum states through wave functions called orbitals. When applied to a particle confined inside a one-dimensional box, it reveals that only standing wave solutions satisfying the boundary conditions are possible. These standing waves lead directly to quantized energy levels and demonstrate that a confined particle cannot possess arbitrary energy or even have zero kinetic energy. The particle in a box model, though simple, forms the foundation for understanding more complex quantum systems such as atoms, molecules, quantum wells, and electrons in solids.